All right, let's dive right in. Today, we're adding a really cool tool to our data analysis toolkit. Think of it like a detective, a specialist that's designed for one super important job, to uncover the truth about whether two different ways of measuring something actually agree. So picture this. You've got a shiny new gadget that measures something faster or cheaper, but you've also got the old, reliable method, the one everyone trusts, the gold standard. The big question is, can you actually trust the new one? How do you know for sure that it's giving you the same results?
And this right here, this is what we call the measurement dilemma. It's a problem that shows up absolutely everywhere, from cutting-edge science labs to everyday decisions. Let's make this super real for a second. Imagine you're comparing a new, at-home blood sugar monitor with the super accurate one at the hospital. For a patient who relies on that number to manage their health, the difference isn't just statistical noise. It's a huge deal. Their health literally depends on those two measurements agreeing.
So, how do we crack this case? Well, it's time to meet our detective, the bland Altman plot. It is the perfect tool for exactly this kind of investigation. So, what is it, really? A bland Altman plot is a way to visually compare two different measurement methods. And the key word here is agreement, not correlation. We don't just want to know if they trend in the same direction, we need to know if they give the same answer. It's also called a difference plot, which is a huge clue about how it works.
And listen, this isn't just some niche medical thing. This tool is a workhorse. It's used in industrial quality control to make sure parts are made to the right spec, and research labs to validate new equipment. Basically, anywhere you need to know if two things are truly interchangeable.
Okay, so we know why we need it. Now let's pop the hood and see how this thing actually works. We're going to break down its anatomy piece by piece. The real magic of this plot is how brilliantly simple it is. On the horizontal axis, the x-axis, you've got the average of the two measurements. You can think of this as our best guess of the real, true value. But the vertical axis, the y-axis, now that's where the investigation happens. It shows the difference between the two readings. It literally plots the disagreement. And building one is really a simple three-step mission. First, for every pair of measurements, you plot 1 point, the average on the bottom, the difference on the side. Step 2, you figure out the average of all those differences and draw it as a straight line across the middle. And finally, step 3, you add 2 more lines, what we call the limits of agreement. These lines create a zone of acceptable error, usually set so that about 95% of your data points should fall inside it if everything's working as expected. Okay, the plot is built. Now for the fun part, the payoff. What clues can our data detective actually dig up? What is this chart really telling us?
The bland Altman plot helps us crack the case in 3 major ways. It lets us see the overall agreement at a glance, it helps us spot any hidden systematic bias, and it points a giant flashing arrow at any suspicious outliers.
Our first clue is the big picture, kind of like a gut check. Just look at the scatter of the points. Are they all packed tightly around that center line? If so, great. That means your two methods agree really well. But if the points are all over the map, that's a red flag that the disagreement is all over the place. Clue number 2 is about finding a hidden bias. Look at that middle line we drew, the mean difference. Is it sitting right on 0, or is it floating above or below? If that line isn't at 0, that's a huge tell. It means one of your methods is consistently measuring higher or lower than the other one. It's a systematic error, clear as day. And our third and final clue, the outliers. These are the smoking guns of your investigation. Any data point that's way outside those upper or lower limits of agreement is screaming for your attention. These points represent a major, unusual disagreement, and you have to figure out what went wrong there.
So you see, when you put all these clues together, you move beyond just raw numbers and start to get a much clearer and more honest picture of what's going on.
It really all boils down to this one simple idea. We're not just collecting data for the sake of it. The whole point is to find agreement, to build confidence in our tools and our results.
So if there's one thing you take away from this, it should be this. By forcing us to look directly at the difference, the bland Altman plot gives a brutally honest look at how well two methods agree. It's way more revealing than just looking at a table of numbers.
And that leaves me with one final thought for you to chew on. No matter what kind of data you work with, it's always worth asking yourself, what hidden biases, what disagreements might be lurking just under the surface? Because sometimes all it takes is the right detective to bring them to light.